Hi, welcome to Calculus 2. Today's topic is integration by parts, the definite integral type. So last time we went through the explanation for what is integration by parts. We wrote all these formulas. I want to do some practice cases where the definite integral is meant. So we have a beginning and end for our region of integration. Aside from that, we are doing the same thing as before. So let's just go ahead and do some basic examples. We have, so suppose I want to integrate from 0 to 1 of tangent inverse of x dx. To make the story short, we can ignore these limits, go ahead and complete the integration and come back and impose 0 and 1 as our limits on the right hand side. Meaning at the beginning we can go ahead and do this to avoid the clutter. We finish the integration, then we come back and impose the limits of the integration at a later stage. So to do that, we are going to be duplicating something that we did, but that's okay. So tangent inverse of x dx without the limits of integral. So next question is, what is our u, what is our dv, or in other words, what's playing the role of f of x and what's playing the role of g prime of x, and so on. Let's go ahead and do one of these approaches, and then I do the other one. Let's go ahead and do this one first. So who is my f? One likely choice is to consider f to be tangent inverse of x, but at the first sight it looks like, well, there's nothing left for g prime. Who's g prime? Well, of course g prime is just the number 1. So if you wish, let's color it. So g prime is being shown by 1. Now we go ahead and actually complete the integration. So I have my f of x taken to be tangent inverse of x, and then for that I need f prime of x. So f prime of x, the derivative of this, you remember from calculus 1, you need to have that table available to you at all times and try to memorize it, of course. And then who is my g prime of x? G prime of x is just 1. What's a function whose derivative is 1? Well, I can write x plus any constant c, but it's better not to clutter this situation. Just leave that out. It doesn't hurt, but doesn't help either, so we might just do away with that. So on the right hand side I have f times g. So f times g, we write g first because there's a simpler function, tangent inverse of x, minus g f prime. So remember, g f prime shows up on the right hand side. So minus g, which is x, f prime is 1 over 1 plus x squared, then dx. Okay, now let me continue here. So I have x tangent inverse of x minus, now I have another integral. Very common situation. We try to do an integral, we end up with another one. The hope is that what is on the showing up on the right hand side is easier, more doable than what we had at the beginning. So should remember this thing from calculus 1. We use a substitution. Well, what substitution? Well, most natural one is to start with the denominator, to avoid the collision with those u's and v's over there. Let me use the letter w here. So I say w is 1 plus x squared. Then the differential of my substitution is going to be 2x dx. Does something like this show up in my integral? Well, I have x dx showing up. So who is x dx? X dx is of course dw over 2. It's half of my differential of w. So again, what we have here is x tangent inverse of x minus, instead of x dx I can write dw over 2, so that is dw over 2, and the denominator is just w. So I integrate that, x tangent inverse of x. Factor of 2 can come outside, so I have 1/2 dw over w. That is, of course, a basic integral is the logarithm of absolute value of w. At the very end, for a indefinite integral, we just throw in a constant. Now we go ahead and write everything in terms of the original variable. We can't use w because we don't know, the reader wouldn't know what's w. W, we introduced it for our convenience, so minus 1/2 of logarithm of 1 plus x squared in absolute value and the constant. Now we have to simplify our answers as much as it can be done. Absolute value here is not necessary because 1 plus x squared is positive all the time anyway, so we might as well clean this up and say x tan inverse of x minus 1/2 of logarithm of, instead of absolute value just write a parentheses plus a constant. So what is this? That's the antiderivative of tangent inverse of x dx. What was our original question? The original question is how about from 0 to 1, if you want a definite integral, if you want a 0 to 1 of tangent inverse of x dx, that means all of these things have to be calculated between 0 and 1. So first let me write all of this, x tangent inverse of x minus 1/2 of logarithm of 1 plus x squared. And if you want to keep the constant, or you want to throw it away, either way, 0 and 1. So I go ahead and calculate it at 1. The 1 tangent inverse of 1 minus 1/2 of logarithm of 1 plus 1 squared plus a constant, that is the contribution from the top part, minus. Good practice is to put subtraction everything in a parentheses to avoid making a mistake of not flipping the sign. So in this case it will be 0 tangent inverse of 0 minus 1/2 of logarithm of 1 plus 0 squared plus a constant. Well, we have this 0. Tangent inverse of 0 is also happening to be 0, so this is definitely all 0. 0 squared of course is 0, plus 1 is just 1. Logarithm of 1 is a 0, so this becomes 0, and of course this whole thing is 0. This constant always cancels the other constant, so from beginning in all the definite integrals you might as well do away with writing the constants. It doesn't help with anything. Another item that we need to remember from trigonometry, what's tangent inverse of 1? Well, that's of course pi over 4. So you might want to refresh your memory about trigonometry, make basic tables of trigonometry and use them. So this becomes pi over 4, and this becomes 1 minus 1/2 of logarithm of 2. So this integral gives us some weird combination of pi and logarithm in the same problem. Now you can apply this limits 0 and 1 to individual pieces or to the whole thing. Either way is fine. So when we write it from A to B and then and then another one from A to B, that is simply doing the same thing to all the functions that are in the site. In practice, perhaps less error prone to find everything. and then apply 0 and 1 to the entire function that you have to avoid the mistake of the most error-prone part of this whole thing is the subtraction. So you have to remember that when you're doing subtraction, all the elements of the second parentheses have to be flipping their signs, and you have to do that carefully. In this case, we couldn't go wrong because everything was 0 anyway, but sometimes it could be different. Let me go ahead and just rewrite this thing one more time with a u and a v notation, just so that you see it's all the same. So if I have tan inverse of x dx, I want to handle that. We said in this uv notation, this is the u tangent inverse of x. dv is that 1 times dx, which is just dv. dv is just dx. Differential of u, that is same as derivative of u times dx, that is 1 over 1 plus x squared. And if dv is equal to dx, v is just equal to x. And again, we don't need to bother with that constant. It doesn't help anything. U times v, sorry, u times v is x tan inverse of x. V du, so here what I'm writing is u, excuse me, let's write this, the order I wrote here, v times u minus integral of v du. So here was u dv, and here is v du. So what's my v? V is x, and du, excuse me, I forgot to write here my differential. V du is x dx over 1 plus x squared, which is just what we said a moment ago, is x tangent inverse of x, and this is 1/2 of logarithm of 1 plus x squared and a constant. So everything same as before, slightly different style of writing. Just make sure you get used to both of them, because your instructor could be using one or the other, and you have your choices in any of these cases. Okay, so that was a simple practice. Let's go ahead and do another one of these problems. For example, 0 to pi of x times sine of x times cosine of x dx. So we have a mixture of sine and cosine in this problem. If you want to allocate some of these functions here to f of x and the remainder to g prime of x, many choices come to our view. You could use f to be x, or x times sine of x, or x times sine cosine, and some of them will lead you to the answer faster than others. And unfortunately, there isn't much of a general rule that will tell you what will succeed, if any, and what will not. So there is always a bit of trial and error involved in all integration problems. You just practice, and you build your judgment accordingly. So this problem, however you approach it, you have to deal with some trig identities, and I might as well start with that identity from the up front, or you might encounter exact same thing further down the calculation. So what identity am I referring to? Sine x cosine s. There is a identity in trig that covers that, and that would be easiest to use up front. Sine of 2x is 2 sine x cosine x. So if you go through your trigonometry book, probably you see I would say about 6 dozen of identities of various form and styles there. You want to have them available to you, and see if one of them comes in handy in some of these problems. So this is one of the basic ones, double angle identity. So let's call it double angle identity. Just to remind you, another version of this thing is for cosine of 2x, even though we are not using it right now. That one has 3 reincarnations. You can write it as cosine square of x minus sine square of x. The way it shows up in calculus is usually under one of these two styles, all cosine or all sine. Either of them is applicable. And there are formulas similar to this for 3x, 4x, and so on. Whole topic all by itself. But let's go back to what is in front of us. How do we handle this? So this, first of all, it can be written as 0 to pi x minus x sine cosine. Sine cosine then of course going to be 1/2 of this. So a factor of 1/2 comes in front, and then I'll have sine of 2x dx. Okay, so a little bit of emphasis that we do need to go ahead and review our trigonometry. Now I come back, listen to the advice that I had over there, that I go after x sine 2x dx, finish this up, and then I come back and take care of all these constants, a factor of 1/2 in front and 0 and pi. This is just general style of trying to reduce the clutter, not to bring too many things all at the same time. Let's go ahead to do the main thing, and these are like garnishing on the side that we can always handle later on. So what do you think? What do you think should be my u and a v and so on? U is chosen to be the function whose derivative is going to be easier than what you're looking at. So the option here is to take u to be x, and dv is going to be whatever is left. Okay, so I didn't take u to be that one as my first attempt, because du is just same weight or same difficulty as u itself. And so that's the advice that we used here. So what happens to du? Of course, du is just dx, and v has to be easy to figure it out here. Antiderivative of this thing, of course, is cosine of 2x over 2. So you have to come up with a function whose derivative will be that. Well, this derivative of this will be off by a minus sign from that, so I need a minus sign. So my v, the function whose derivative is sine of 2x, again, one of the basic integration formulas from calculus 1. You have to have this under control. And again, as we said, that extra constant here is not going to help. So x times that is going to be minus x cosine of 2x over 2. Notice I put the minus up front, otherwise it's going to look like you're subtracting things. You're multiplying them. One of them is negative, so you bring the constants up front. Minus x cosine of 2x over 2, and then minus v du. v du is minus cosine of 2x over 2 dx. Let's separate these things. So minus x cosine of 2x over 2, minus and minus becomes a plus, a factor of 1/2 can move outside, and I'll have cosine of 2x dx. Antiderivative of cosine is basic from calculus 1. So antiderivative of that will be sine of 2x over 2, and the two factors, 2 and 2 makes a 4. That's a sine of 2x. And if we were dealing with indefinite, there will be a constant. If you're doing definite, you don't need to worry about that constant. So if I was doing from 0 to pi of x sine of x cosine of x dx, I just put all of this minus x cosine of 2x over 2 plus a quarter of sine of 2x. We said no reason to bother with that c anymore, 0 and pi, and I put a pi in this, so minus pi cosine of 2 pi over 2, 1 quarter of sine of 2 pi. Put everything in the parentheses so that it looks like it's contribution from upper limit. 0 minus 0 cosine of twice 0, 1/4 of sine of twice 0 is just 0. Now remember, cosine of 0 is 1, but since we multiplied by 0, this is whole thing is 0. Sine of 0 is also 0, so we got lucky that everything on the second contribution all became 0, nothing significant there. Cosine of 2 pi. What's cosine of 2 pi? Cosine of 2 pi is 1, of course. How about sine of 2 pi? Sine of 2 pi is 0. Again, you need to have your tables of trig values for all famous angles listed so that in case you need to consult them, but try to build it in as it becomes second nature. So I'll have minus pi over 2 as my answer. Okay. Okay, except that I noticed that I made a mistake. Let me go ahead and correct myself by doing it in red. So let's see. The problem became a bit lengthy, so I forgot that when we did this, a factor of 1/2 was in front of this. So whatever I calculated here, this was for this integral, and I have to multiply it by a factor of 1/2, so I have to have a factor of 1/2 in front of all of this, and that means a factor of 1/2 in front of everything I had here, and a factor of 1/2 in front of what I have here. So it all boils down to minus pi over 4. So sorry for that. I forgot that factor of 1/2. So again, the correction is a factor of 1/2 to multiply by this. It has to be multiplied here, and all the way through all of the calculations needed a factor of 1/2. Okay. So that was one other example. Okay, so let's do one more example. Change my color again. Sorry. So here the example: 0 to 1 r cubed over square root of 4 plus r squared dr. The main issue here is how to detect u and dv, or f and g prime, and so on. So again, there are many ways of breaking this into two pieces. What is the method to go through? Here I write it like this: r squared times another r over radical 4 plus r squared. Why do I do like that? Because I'm hoping that the fact that derivative of this expression in the radical is showing up here is going to help me with all the steps of integration. Again, it's not a guarantee that this is going to work, but that's the basis by which I proceed. So I'm going to take u to be r squared, and then dv is going to be whatever is left, r dr over square root of 4 plus r squared. Now du is straightforward, it's just 2r dr. question, what is V? That is a separate integration problem all by itself, albeit easier than what we have over there. So I need to integrate this thing to find what is my V. R over radical 4 plus r squared dr. Who is that? Well, this falls in calculus 1, that we use substitution, which W is 4 plus r squared. So dW is obviously 2r dr. So everything looks like working. This is my radical W. R dr is half of my dW. So I write 1/2 of dW. That's for my numerator. And this is radical W. That is. So I put the 1/2 outside, and then W to power of minus 1/2. And then I'll have dW, so 1/2 of exponent of W goes up by 1, becomes plus 1/2, divided by 1/2, and we don't deal with the constant anymore. 1/2 and 1/2 cancel. W in radical, so 4 plus r squared. So my V is, after all that works, so we have an integration problem inside another integration problem. Now what do I have? R u v, so that's going to be r squared, the radical 4 plus r squared, minus v du. Minus v du, that's going to be 2, I write the simple portion first, 2r v radical 4 plus r squared dr. So this is u dv, excuse me, v du. I wrote the pieces in the traditional style, which is smaller items first and more complex items later on. Now I have to calculate that integral. Well, that one looks very similar to this. Let's write it here. I have 2r radical 4 plus r squared. Use the exact same thing, so this is dr, of course. 2r dr, that's my dw, that's what we see here. And this is radical W, so of course you write it W to power of 1/2 dW. Use the power law, so W to power of 1 plus 1/2 is going to be 3/2 divided by 3/2. So that's going to be written as 2/3 of, or W was 4 plus r squared to power of 3/2. Okay, so what happens after this? Let me write this. The expression above is radical r squared times radical 4 plus r squared, and the second piece is minus 2/3 of 4 plus r squared to power of 3/2. So let's write this, what we obtained so far. So r cubed over radical 4 plus r squared became r squared radical 4 plus r squared minus 2/3 of 4 plus r squared to power of 3/2, and a constant. I should have added a constant here. Now if I want to calculate from 0 to 1, well, I'll have all of this 4 plus r squared minus 2/3 of 4 plus r squared to power of 3/2, calculated between 0 and 1. C, of course, cancel, sorry. At 1, I have 1 times radical 5 minus 2/3 of, this is again 5 to power of 3/2. This is at 1. At 0, this is obviously 0, minus 2/3 of, this is 4 to power of 3/2. Let's clean up. Radical 5, 5 to the power of 3/2. That's of course 5 times radical 5. 5 times 5 to the power of 1/2. So twice that becomes twice this 5 becomes 10^3, and this one I write it as radical 5, so it looks like this, minus another minus becomes plus 4 to the power of 3/2. Of course that's just 8. Square root of 4 cubed becomes 8 times 2 becomes 16^3, and so taking common denominator here, 3 minus 10 becomes minus 7/3 of radical 5 plus 16^3. Cleaning it up, perhaps we factor a third out, and 16 minus 7 radical 5 is what's left. Okay, rather lengthy, but that's what this beast is like. It takes a bit of time and practice. So notice that for your homework, what is expected is that you show the steps of derivation. So if we were coming to say this problem, starting from here and all of a sudden magically coming to this answer, that would not be the style of this course. You want to show all the substitutions step by step, what you did, and like that. Okay, until next time, good luck and God bless.